Hello everyone, I'm Guo, a PhD student from East China Normal University. Now, I will introduce my work, Optimizing Input Minimization in Kernel Fuzzing. As the core component of an operation system, the kernel manages underlying hardware resources while offering an execution environment for upper-layer applications. Once a kernel vulnerability is exploited by hackers, all the applications will be affected, causing system-wide domino effects. To this end, coverage-guided kernel fuzzing has emerged as one of the effective approaches for discovering kernel bugs. For example, SetsColor, the most popular and representative coverage-guided kernel fuzzing, has successfully uncovered over 5,000 bugs in Linux kernel. Generally, coverage-guided kernel fuzzing usually includes two major stages: mutation and minimization. The mutation stage aims to mutate seeds to find interesting programs. Since the new inputs are randomly generated, they may contain redundant system call or arguments. Therefore, an important stage, minimization, is adopted to remove coverage-irrelevant calls and arguments to improve the mutation efficiency. So, the minimization stage is critical in the kernel fuzzing. Take SetsColor as an example. It adopts a one-by-one minimization strategy to remove irrelevant calls and arguments. For call removal, the goal is to remove irrelevant calls while preserving the new coverage of target call. For this interesting program, it has 5 calls, and the last call, call 5, is the target call, which achieves the new code coverage. First, the one-by-one call remove call 1 and execute to verify call 5's coverage is returned. Assuming this attempt is failed, the program roll back to orange program and remove call 2. Assuming this attempt is successful, the call 2 will be removed, and then remove call 4 and execute to verify the call 5's coverage is returned. Assuming this attempt is success, and finally, the program becomes C1 and C5. So, in this way, one-by-one call remove consumes 4 executions. Next, the next step is to simplify the arguments. For the argument simplification, the goal is to simplify each argument while preserving the new coverage of target call. For the program after call minimization, it has 2 calls and 3 arguments. First, the argument simplification simplify A1 and execute to verify call 5's coverage is returned. If this attempt is successful, A1 becomes A1 apostrophe. Then, in the same way, it tries to simplify the resource argument R1. If this attempt successful, R1 becomes R1 apostrophe. Then simplify the argument A4. Finally, the program becomes this. So, in this way, the one-by-one argument simplification consumes 3 executions. So, for SetsColor, the one-by-one minimization strategy consumes a total 7 executions to remove irrelevant calls and irrelevant arguments. However, we observe a significant tension between the benefit and cost of the minimization stage. We we run syscaller and syscaller minus for 48 hours. While syscaller we configure with minimization stage and syscaller minus without minimization stage. We count the branches and unique bugs to observe their effectiveness. As a result, without minimization stage, the coverage and the number of found unique bugs decrease by 27.5% and 40.4%. In this experiment, we count the proportion of program executions as the cost of minimization stage and the mutation stage, because each mutate or minimize require one program execution to verify the target call is returned. So, the result shows the proportion of program execution during minimization stage accounts for 57.5%, leading to significant costs. So, the minimization stage can improve the effectiveness of kernel fuzzing, while it also consumes over half of the fuzzing resource. To mitigate the tension, the key challenge is how to reduce the minimization cost while keeping the minimization benefits. To mitigate this tension, our idea is to reduce the number of program executions for verifying whether new coverage is preserved. The fewer the program executions are, the lower the cost is. To implement this idea, we designed two optimization strategies: influence-guided call removal and type-informed argument simplification strategy. The influence-guided call removal strategy is to remove the number of program execution during call removal. The type-informed argument simplification strategy is to reduce the number of program execution during argument simplification. The results shows our optimization strategy can reduce the minimization cost of syscaller by 16.7%. For the influence-guided call removal strategy, our insight is irrelevant calls can be removed at once rather than one by one, as they does not affect the new achieved coverage. Take the interesting program as example. We assume call 2, call 3, call 4 does not affect call 5. So, we remove call 2, call 3, call 4 at once rather than one by one, and execute to verify call 5's coverage is returned. Assuming this attempt is successful, the program becomes call 1 and call 5. Then, we attempt to remove call 1 and execute to verify call 5's coverage. Assuming this attempt is failed, so the final program has two calls. So, the influence-guided call only consumes two executions to minimize the irrelevant calls. Compared to one-by-one strategy, our influence-guided strategy can reduce the program execution by 50%. For the type-informed argument simplification strategy, our insight is that only need to simplify the redundant arguments or their subfields that truly matter for the subsequent mutations. For the program after call minimization, there has two calls and three arguments. argument A1 is an integer type, and R1 is a resource type, and A4 is an element of array type. So we can skip the simplification of integer A1 and resource argument R1, as simplify len does not reduce subsequent mutation space. So we only simplify A4 and execute to verify call 5's coverage is retained. Assuming this attempt is success, so the program becomes this. As a result, our type-informed strategy only need one program execution to reduce the irrelevant arguments. It can reduce the program execution by 66% compared to one-by-one argument simplification. In sum, our two optimization strategy only require 3 program execution, while the one-by-one strategy require 7 program executions. So our strategy can reduce the number of program execution by 57.1%. We implement the two strategies in this column. As we can see, the influence-guided call remove strategy replaces with the one-by-one call remove, and the type-informed argument simplification strategy replaces with the one-by-one call argue simplification. We also collect influence relation to infer the irrelevant call. We define the influence relation as the effect of two calls on execution paths. We use static analysis to collect 14,400 and 966 static influence relation. We also use dynamic analysis to collect 29,000 and 899 influence relation. We use the default branch coverage to record the execution information of each call. For the evaluation, we first evaluate the effectiveness of SysMini in terms of the achieved code coverage and the number of found unique bugs and the hidden run and time to exposure. For the setup of RQ1, we compare SysMini to syscaller on 3 Linux versions. Each tool runs 24 hours and repeats 10 runs. We count the achieved code coverage and the number of unique bugs. We also count the hidden run and time to exposure for each bug. For the code coverage, as we can see, SysMini has achieved 13.3% and 20.2% and 20.1% coverage improvement on 3 kernel versions. For the number of found unique bugs, we can see SysMini has found 2.0 times, 1.7 times, and 2.0 times unique bugs than syscaller on the 3 kernel versions. For the hidden run and the average TTE of each common bugs, in this picture, SK denote the syscaller, SM means SysMini. As we can see, among 22 common bugs, SysMini can find them fast, and more frequently than its color. We also evaluate the applicability of our two optimization strategies for different kernel fuzzings. Vegas is a tool that utilizes reinforcement learning to improve the kernel fuzzing effectiveness. Cutdown, which is a tool to find memory-related bugs. Direct, is a directed kernel fuzzing tool. For the setup of ARC2, we have implemented our strategies in Vegas, Cutdown, and Direct. We call them Vegas Plus, Cutdown Plus, and Direct Plus. We compare Vegas with Vegas Plus in terms of code coverage and the number of unique bugs. We use the memory-related bugs to evaluate Cutdown and Cutdown Plus. We use the average TDE and hitting round for comparing Direct and Direct Plus. For Vegas and Vegas Plus, as we can see, Vegas Plus can improve branch coverage by 14.5% and found 2.0 tons unique bugs on average. For Cutdown and Cutdown Plus, we can see Cutdown Plus achieves 66.7% improvement in terms of cancel bugs. For Direct, we can see Direct can reproduce the bugs with less time than Direct. Also, for the hitting round, Direct Plus reproduced 1.5 times bugs than Direct and found them more frequently. Okay, finally, our tool Mini has been open sourced at GitHub. The scholar Ting has already implemented our optimization strategy in its latest version. Because my visa states are still in check, so I can't attend to this meeting. If anyone have questions about our work, you can contact me by this email. Thanks.